You've Googled Poisson Distribution. You got hit with a wall of formulas, probability density functions, random variables. It felt abstract. It felt useless. You're trying to solve a real problem, like why customers arrive in clumps at your coffee shop. And the textbook gives you Greek letters. Let me tell you something. You are learning probability all wrong. Here's the truth. These aren't abstract concepts. They are the hidden patterns in everything around you. Customer arrivals at Starbucks? That's Poisson. Test scores in your class? That's the normal bell curve. A defective part in a factory batch? That's binomial. Forget the confusing textbooks. Give me 50 minutes, and you will master the 10 distributions that run the world. No confusion, just raw intuition, built from the ground up. Now, take a look at this. These are the 10 distributions we're going to master. In Part 1, we'll cover the basic and counting distributions. Check out the table. You can see things like uniform, Bernoulli, binomial, and of course the famous normal bell curve. Then, in Part 2, as you can see in this next table, we'll get into the growth and waiting time distributions. This is where we cover things like the lognormal, geometric, Poisson, and exponential. And here's the secret nobody tells you. They are all connected. Look at this diagram. The Bernoulli is the single atom that builds the binomial. And the binomial, when you scale it up with enough trials, actually becomes the normal distribution, that perfect bell curve. And then there's the Poisson, which is linked directly to the exponential. One counts events, the other measures the time between them. They're two sides of the same coin. You see, you won't just memorize 10 formulas. You will understand the system of randomness. You will learn to speak its language.
Let's start with the absolute foundation. We're going to begin with two distributions that seem almost too simple. The uniform and the Bernoulli. So why are we starting here? Because one is the atom of randomness, and the other is the atom of decision. Every single complex pattern we're going to discuss is built from these two fundamental ideas. Master them, and the rest will just click into place. First up, the uniform distribution. You can think of this as the atom of randomness. This is the source code of randomness. When your computer runs a rand function, it's using a uniform distribution. The key idea? Every outcome is equally likely. Let's make this real with an example I call the waiting game. Imagine a bus that arrives anytime within a 10-minute window. Not a single second is more likely than any other. When you visualize this, the probability shape is just a flat line, a rectangle. Now, the formula for this is called the probability density function, or PDF. Take a look at it on the screen. I know, it's our first formula. Don't panic. For our bus arriving between time A equals 0 and B equals 10, the formula is just 1 divided by 10 minus 0, which gives us 1/10. See? This formula is just drawing that flat line for us at a height of 1/10. The only rule for any PDF is that the total area under the curve has to equal 1, representing 100% probability. Let's check if our rectangle works. The width is 10 minutes. The height, as we just saw, is 1/10. So the area is width times height, 10 times 1/10, which equals 1. It works. All right, let's solve a problem. The bus arrives anytime in that 10-minute window. What's the probability the bus arrives between minute 3 and minute 7? You don't need calculus for this. It's just a rectangle. The width we care about is 7 minus 3, which is 4 minutes. The height is still 1/10, so the probability, which is the area, is just 4 times 1/10. That gives us 4/10 or 40%. And that's it. You just mastered the uniform distribution. So what about the simplest possible event? A single yes or no question. A user clicks an ad, or they don't. A patient responds to a drug, or they don't. A coin flip comes up heads, or it's tails. This is the Bernoulli distribution, the atom of decision. It's a single experiment with just two outcomes, and it's defined by only one parameter, p, which is the probability of success. Now, check out this table. We code a success as the number 1, and its probability is p. We code a failure as the number 0, and its probability is 1 minus p. Now, mathematicians cooked up this single formula you see here, the probability mass function, or PMF, to express both of those lines at once. This looks way more complex than it is. It's just a clever trick. Let's prove it's just a machine that spits out the right probability. We'll walk through this together.
First, what's the probability of success, where k equals 1? We plug 1 into the formula. We get p to the power of 1 times 1 minus p to the power of 1 minus 1. That second term becomes to the power of 0, which is just 1. So we're left with p. Correct. Now, what's the probability of failure, where k equals 0? We plug in 0. We get p to the power of 0 times 1 minus p to the power of 1 minus 0. P to the 0 is just 1. So we're left with 1 minus p. Correct again. A single coin flip is simple. But its true power is as a building block. You don't really care if one person opens your email. You care how many open it out of the 500 you sent. This is the job of the binomial distribution. It counts the number of successes and a fixed number of independent Bernoulli trials. And it's described by this beast of a formula. Check this out. I know, that looks like a mess. Greek letters, factorials. It's why people quit stats. But don't you dare close this tab. This formula tells a simple, two-part story, and we're going to build it from scratch, right now. Okay, let's build the binomial formula. We'll start with a question. What's the probability of getting exactly 2 heads in 3 coin flips with a fair coin? So we've got our variables. K is 2 successes, N is 3 trials, and P is 0.5. Let's look at part 1, the probability of one sequence. Imagine just one specific way this could happen, like heads, heads, tails. Because each flip is independent, we can just multiply the probabilities. So the probability of heads times the probability of heads times the probability of tails. That's 0.5 times 0.5 times 1 minus 0.5. Look at how that's written on the slide. It's 0.5 squared times 0.5 to the power of 1. This is the general pattern you'll see every time. P to the power of k times 1 minus p to the power of n minus k. And that's the entire second half of our scary formula. It's just the probability of one specific combination of successes and failures. Now for part 2, the number of ways. Getting heads, heads, tails isn't the only way to get 2 heads. We could also get, as you see here, heads, tails, heads, or tails, heads, heads. There are 3 ways. This is a combinations problem. From n slots, how many ways can you choose k of them to be successes? And look at the formula for n choose k. For our coin flip, that's 3 choose 2, which comes out to exactly 3. And that's the first half of our formula, the number of ways you can arrange the successes. So you've done it. You've built the formula. It's just the number of ways it can happen times the probability of any one of those ways happening. Look at it now. It's not scary anymore. It's a story. All right, let's solve a real problem. Your new marketing email has a 2% open rate. You send it to 500 people. What's the probability that exactly 12 people open it? Let's set it up. N is 500, P is 0.02, and K is 12. We just plug it into the formula. As you can see, that's 500 choose 12 times 0.02 to the 12th power times 0.98 to the 488th power. The answer comes out to about 10.8%. But here's the most useful part: the average, or what we call the expected value. And it's incredibly intuitive. The mean is just N times P. So for our campaign, you'd expect 500 times 0.02, which is 10 opens. Simple. The binomial is perfect for two outcomes: success or failure, heads or tails, clicked or not clicked. But what happens when there are more than two options? Time to level up: the multinomial distribution. And here's the best part: the logic is exactly the same. I'm serious. It's still just the number of ways times the probability of any one way. Now, look at this formula. I know, it seems even worse, but you already have the intuition to decode it. It's the same two-part story. Let's look at the pattern. First, the probability part. Instead of just p to the k, we just multiply the probability of each category, raised to the power of how many times it occurred. Makes sense, right? Second, the counting part. Instead of n choose k, we use this thing called the multinomial coefficient. It's just a generalized way of counting arrangements when you have multiple groups. Same idea, just bigger. Let's try a problem. A factory produces shirts in 3 colors: 50% red, 30% blue, and 20% green. You pull 10 shirts randomly. What's the probability you get exactly 5 red, 3 blue, and 2 green? Let's set it up. N is 10. Our K values are 5, 3, and 2. And our probabilities are 0.5, 0.3, and 0.2. We plug it into the machine. Look at the screen. 10 factorial over the product of the individual factorials, times each probability raised to its count. The answer is about 8.5%. And that's it. You just went from a simple coin flip to modeling complex multi-category outcomes in minutes. What happens when the number of trials n gets astronomically large? Calculating the binomial for 10,000 coin flips would be a nightmare. But you don't have to. The jagged bars of the binomial histogram begin to blur. They smooth out into a perfect, elegant shape. This is the most famous, most powerful pattern in all of statistics: the bell curve. Let's watch this happen. Here's the probability of getting heads in just 10 coin flips. As you can see, it's a bit jagged. Now, let's ramp it up to 100 flips. Better. It's starting to take on a familiar shape, isn't it? And now, 10,000 flips. The bars blend into a perfect, smooth curve. This isn't a coincidence. This is a fundamental law of the universe. This shape is the normal distribution, and it's governed by one of the most powerful ideas in all of mathematics, the central limit theorem. You can call it the one theorem to rule them all. It states that when you sum up lots of independent random events, no matter what their individual distributions look like, their combined effect will always trend towards this perfect bell curve. This is why it's everywhere. Human heights, that's the sum of thousands of factors. Normal. Lab measurement errors, just the sum of tiny disturbances. Normal. The average of a poll, it's the sum of many opinions. Normal. It's the pattern of averages. And it's completely defined by just two things. First, mu, the mean, which sets the center of the bell. And second, sigma, the standard deviation, which controls the width or the spread. Now, you've probably seen the formula. And let's be honest, it is the stuff of nightmares. Look at this thing. But do not panic. You don't need to memorize this. You just need to understand what each part does. Think of it as a machine with 3 parts. Check out this diagram. The first part is the distance engine. It just asks, how far is my point from the center? The second part is the bell-shape creator. That little e raised to a negative power creates the signature drop-off. And the third part, the scaling factor. It's just there to make sure the total area under the curve equals 1. That's it. So, it's not a monster. It's a machine for drawing a bell. But this machine created a huge problem. To find a probability, you have to solve this impossible integral you see on the screen. This integral has no simple solution. Before computers, this was a disaster. Statisticians needed a miracle. And they found one, the z-score. The z-score is a universal translator. It transforms any normal distribution into the one standard normal distribution, with a mean of 0 and a standard deviation of 1. Here's the key formula for it. All this asks is, how many standard deviations is my point x away from the mean? That's all it's doing. Because of this, we only need one table to solve any normal distribution problem. This was the breakthrough. Here's a piece of that table, the standard normal z-table. Let's see what it tells us. Let's start by calculating the area within one standard deviation. We need to find the probability between z equals 1 and z equals -1. So we look up p of z less than 1.0 and p of z less than -1.0 in our table. We get 0.8413 and 0.1587. We subtract them and get about 68%. Now, let's do it for 2 standard deviations. The process is the same. We look up 2.0 and -2.0, subtract the probabilities, and we get about 95%. See the pattern? Okay, one last time for 3 standard deviations. We look up 3.0 and -3.0, subtract, and we get 99.7%. This gives us the famous 68 to 95 to 99.7 rule. About 68% of all data falls within one standard deviation of the mean. 95% falls within 2 standard deviations, and 99.7%, almost everything, falls within 3. Let's solve a real problem. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What is the probability of a person having an IQ of 130 or higher? Step 1. Translate to the z-world. We use our z-score formula. That's 130 minus 100, all divided by 15. So 30 divided by 15 gives us a z-score of exactly 2.0. This means an IQ of 130 is exactly 2.0 standard deviations above the mean. Step 2. Rephrase the question. Our question is now simply, what's the probability of z being greater than or equal to 2.0? Step 3. Look up the answer. Remember, the table gives us the area to the left. Looking at the table for a z-score of 2.0, we find the probability is 0.9772. But we want the area to the right, the chance of an IQ greater than 130. So we just do 1 minus 0.9772, which equals 0.0228. The answer is 2.28%. You just solved the impossible integral without doing any calculus. That's the power of the z-score. Let's quickly check our work with the 68 to 95 to 99.7 rule. We know about 95% of people have an IQ between 70 and 130. That's 2 standard deviations on either side of 100. This means 5% is outside this range, with 2.5% in each tail. Our answer of 2.28% for scores above 130 fits this rule perfectly. The normal distribution is king for things that are added together. But what happens when you multiply them instead? Think about it. Your investment portfolio grows by a percentage. That's a multiplication. City populations, biological cells, your own income, they all grow multiplicatively. When you multiply many small random factors, you don't get the symmetric normal bell curve. You get its twisted cousin, a skewed, long-tailed distribution. The signature pattern of growth and money, the Lognormal Distribution. If you look at the shape of the lognormal, you'll notice the long right tail. This is exactly why a few people can earn exponentially more than the average. Now, this distribution comes with a truly monstrous formula. Check this out. It's a lot. But what if I told you that you'll never need to use it? Because there is one simple, elegant secret that makes any lognormal problem trivial. This is the only thing you need to remember. A variable, let's call it x, is log-normally distributed if its natural logarithm, ln of x, is normally distributed. Look at the formula again. See the ln x part highlighted? That's the key. That's it. That's the entire hack. The lognormal is just a normal distribution that's been warped by the exponential function. This gives us a powerful three-step strategy: transform, solve, and conquer. You don't fight the lognormal beast in its own territory. Number. You transform the problem into the simple normal world, solve it there, and you're done. Let's prove how easy this is with an example. Here's the problem. In a certain city, annual income is log-normally distributed. Now, if we take the log of everyone's income, we get a nice normal distribution with a mean of 11.2 and a standard deviation of 0.75. The question is, what percentage of households earn more than $100,000? Let's use our strategy. Step 1. Transform the boundary. We don't want to work with $100,000 in the log-normal world, so we transform it into the log world. The natural log of 100,000 is about 11.51. As you can see in this diagram, our question about income being greater than $100,000 in the log-normal world has now become a question about the log of income being greater than 11.51 in the normal world. Now for step 2. Solve the normal problem. Our complex question is now simple. What is the probability that a normally distributed variable with a mean of 11.2 and a standard deviation of 0.75 is greater than 11.51? This is a job for the z-score. As you see in the formula, we take our value, 11.51, subtract the mean, 11.2, and divide by the standard deviation, 0.75. That gives us a z-score of about 0.413. And finally, step 3. Conquer with the z-table. We need to find the probability that z is greater than 0.413. A z-table tells us the area to the left of 0.413 is about 0.66, or 66%. But we want the probability of being greater than that. So we do 1 minus 0.66, which gives us 0.34. The answer? Approximately 34% of households earn more than $100,000. We tamed that complex, skewed distribution without ever touching its nasty formula. We just took the log, and it became a simple z-score problem. This is why the log-normal is so critical in fields like finance, where it's used for stock prices in the famous Black-Scholes model. In economics, it describes income distributions where billionaires create those long tails. And in biology, it models the sizes of organisms that experience multiplicative growth. There's a totally different kind of question we can ask. Instead of asking, how many successes will I get in 10 tries? We can ask, how many tries will it take me to get my first success? This is the world of waiting time distributions. And the simplest, most fundamental one is the geometric distribution. It models the number of trials you need to get your very first success. And the best part? To derive it, you just need to think for 2 seconds. Seriously. Let's look at the derivation using just common sense. What has to happen for your first success to be on trial number k? Think about it logically. 2 things must be true. First, you have to fail on every single trial before trial k. That's k minus 1 failures in a row. Second, you have to succeed on trial k. Okay, let's write that down with probabilities. Check this out. The probability of k minus 1 failures is just 1 minus p multiplied by itself that many times. So that's 1 minus p to the power of k minus 1. And the probability of that one success? Well, that's just p. Since the trials are independent, you just multiply them together. And here's the formula. The probability that your first success is on trial k equals 1 minus p to the k minus 1 times p. We see the 2 parts right there. The k minus 1 failures and the 1 success. That's it. No combinations, no factorials, no weird constants. Just the raw probability of the one sequence that matters. Fail, 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 succeed. Let's try a problem. We have a salesperson with a 10% chance of closing a deal on any given call. So P is 0.1. The question is, what's the probability their first successful sale happens on their 5th call? So K equals 5. Let's look at the setup. Our success probability P is 0.1. So the failure probability, 1 minus P, is 0.9. And we're looking for the first success on trial K equals 5. This means they must fail 4 times, then succeed once. So we plug that into the formula we just made. It's 0.9 to the 4th power for the 4 failures, times 0.1 to the 1st power for that 1 success. This comes out to 0.6561 times 0.1, which gives us 0.06561. So there's about a 6.6% chance of this happening. Now for the best part. This is the most beautiful formula in probability. The average or expected number of trials you have to wait. Look at this. It's just 1 divided by p. This is one of the most elegant and beautiful formulas in all of probability. It just makes perfect sense. Let's test the intuition. If your success rate is 10%, or p equals 0.1, which is 1/10, how long would you expect to wait? Well, the mean is 1 divided by 0.1, which is 10 trials. Of course, if you succeed 1 out of 10 times, you expect it to take 10 tries. What if a player has a 50% free throw percentage? So P is 0.5. How many shots until their first basket? 1 divided by 0.5 is 2 shots. Of course. It's simple, intuitive, and incredibly useful for modeling all sorts of things. Like the number of calls to get the first yes, the number of items you test before finding the first defect, or, my personal favorite, the number of times you have to fight a boss in a video game to get that rare item drop. The geometric distribution handles the first success. But what about waiting for multiple successes? Think about a sales quota of 5 sales, or finding 10 tagged fish for a scientific study. We need to go from waiting for the first success to waiting for the nth success. This is the job of the negative binomial distribution. Now, when you look at the formula for it, check this out. I know, that looks like we're back in scary formula land. But I promise you, you already know how to solve this. This formula is just 2 ideas we've already mastered, smashed together. So let's build the formula together. What has to be true for your nth success to happen on trial K? There are really 2 conditions that have to be met. First, let's talk about condition 1, the grand finale. The kth trial, the very last one, must be a success. That's the one that gets you to your goal. The probability of that single event is simply P. Okay, that's one piece of the puzzle. Now for condition 2, the setup. In the K-1 trials that came before the final one, you needed to have exactly R-1 successes. You had to be perfectly set up, waiting for that final win. So, what's the probability of getting exactly R-1 successes in K-1 trials? Does that sound familiar? Getting K successes in N trials? That's the binomial distribution. It's a problem you've already solved. We just plug our new numbers into the binomial formula we already know. Look here. Our n is now k-1, and our k is now r-1. When you plug those in and simplify, you get this expression right here. Now, just combine the setup with the grand finale. We take the binomial part for the setup and multiply it by the probability of that final winning success, which is just p. Combine the p terms, and you get the full formula. It was just a binomial problem in disguise. See? Not so scary. Let's try a problem. A basketball player makes 80% of her free throws, so P is 0.8. What's the probability she makes her third basket, so R is 3, on her fourth attempt, where K is 4? Let's break it down using our 2 conditions. First, the final shot, shot number 4, must be a make. The probability of that is 0.8. Second, in the first 3 shots that came before it, she must have made exactly 2. This is just a little binomial problem. So for that binomial part, the probability of getting 2 successes in 3 trials is combinations of 3 choose 2 times 0.8 squared times 0.2 to the power of 1. That comes out to 0.384. To get the total probability, we just multiply the binomial part by the final shot's probability. So 0.384 times 0.8, which equals 0.3072. There's a 30.72% chance. Now the expected waiting time, the mean, is just as elegant. Look at this formula. The mean is just R divided by P. This makes perfect sense. If you wait 1 over P for one success, like in the geometric distribution, you'd expect to wait R times longer for R successes. Let's go back to our sales quota example. A salesperson has a 10% close rate, so P is 0.1, and a quota of 5 sales, so R is 5. Their expected number of calls to hit that quota is 5 divided by 0.1, which is 50. 50 calls. It makes perfect sense. We've now mastered waiting for successes in a sequence of discrete trials. Flip 1, flip 2, flip 3. Call 1, call 2, call 3. But many of life's events don't happen in neat numbered trials. Customers don't arrive at a coffee shop in trials, they just arrive. Emails don't hit a server in trials, they just appear. Accidents on a highway don't happen in trials, they happen over time. These events occur over a continuous interval. not in a sequence of tries. We need a new tool. So let's do a thought experiment. It's one of the most beautiful derivations in all of statistics. What happens if we take the binomial distribution and push it to its absolute limit? What if we have a huge number of trials where n approaches infinity and a tiny probability of success in each trial where p approaches 0? But, and here's the key, we do it in such a way that the average number of successes, lambda, which is just n times p, stays constant. Think of it like this. In any given second, the chance of a customer arriving, p, is almost 0. But there are infinite seconds in an hour. That's our number. The result is a steady average, our lambda, of maybe 10 customers per hour. This transforms the lumpy, discrete binomial into a smooth, powerful tool for modeling rare events. This is the origin story of the Poisson distribution. So where does Poisson's formula actually come from? You've probably seen it before. Look at this formula on the screen. It looks like it came from another planet. Where did that e come from? Why is there a factorial? Well, it's not magic. It's the ghost of the binomial distribution. And we're going to derive it in 60 seconds. First, let's start with the binomial formula. Check it out on the slide. We begin with our old friend, the binomial PMF, and we just substitute p with lambda divided by n. Okay, step 2. Simplify the success part. We're going to rearrange the terms. Look at how we've rewritten the expression. Now, here's the trick. As n gets infinitely large, that first term, the n times n minus 1, all over n to the power of k, what happens to it? Think about it. When n is a trillion, n minus 1 is basically still a trillion. The entire first term just becomes 1. So we're left with just the lambda to the k over k factorial part. Simple enough. Now for step 3. Simplify the failure part. The last piece of the puzzle is this term here. Since n is huge, that little minus k at the top is like a drop in the ocean. We can just ignore it. So we're left with this expression. Does that look familiar? This is one of the fundamental definitions from calculus. It's the limit that defines the exponential function, e. In our case, x is equal to negative lambda. So our entire failure term just becomes e to the power of negative lambda. And now, for the grand finale. Put the two pieces together. The success part became lambda to the k over k factorial. The failure part became e to the negative lambda. And there it is, the Poisson formula. It's not arbitrary. It's the mathematical destination of counting successes when the trials become infinite and the events become rare. So, how do you actually use it? The Poisson distribution is defined by a single parameter, lambda. That's the average number of events in a given interval. It answers the question, if the average is lambda, what's the probability of observing exactly k events? Let's try a problem. A support center receives an average of 5 calls per hour, so lambda is 5. What's the probability they receive exactly 2 calls, so k is 2, in the next hour? We just plug it into the formula. Look at the screen. We take 5 squared times e to the negative 5 and divide it all by 2 factorial. That gives us 25 times about 0.00674 divided by 2. The final answer is about 0.084, or 8.4%. Now here is the golden rule of Poisson. You have to remember this. Your lambda must match your interval. So, if you want to find the probability of getting 1 call in the next 30 minutes, or 0.5 hours, you have to scale your rate. Your new lambda would be 5 calls per hour times 0.5 hours, which gives you a new lambda of 2.5. Always match the rate to the interval. And here's the most important practical takeaway of this whole chapter. For a Poisson process, the mean is lambda, and the variance is also lambda. The mean is equal to the variance. This is the signature of a Poisson process. So if you're looking at real-world count data and you find that the mean and variance are roughly the same, you should immediately think Poisson. It's your diagnostic tool. You'll see this used everywhere, in operations, for customer arrivals, support calls or inventory requests, in IT and DevOps, for server requests or bug reports per day, and even in biology, for modeling things like DNA mutations or radioactive decay events. The Poisson distribution is incredibly powerful. It counts how many rare events happen in a continuous interval. This leads to the next, most logical question of all. We know how to find the probability of 5 customers arriving in an hour, but how long do we have to wait between customer number 1 and customer number 2? If the count of arrivals follows a Poisson process, then the time between those arrivals follows its beautiful, continuous counterpart, the exponential distribution. It's the other side of the Poisson coin. Look at this comparison on the screen. The Poisson counts events in an interval. The exponential measures the gap between those events. And the formula for it isn't something you have to memorize. It's something you can derive right now with a single, brilliant insight. So here's the brilliant insight. Let's ask a question. What is the probability that the waiting time, which we'll call capital X, is longer than some amount of time, little x? If you've waited for X minutes and the event still hasn't happened, what does that mean? It means there were 0 events in that time. So these two questions are the exact same thing. What's the probability the waiting time is longer than X is identical to what's the probability of having 0 events in an interval of length X? And we have a tool for that second question. It's the Poisson formula we just learned. Let's derive this together. We want the probability of 0 events, so k equals 0 in an interval of length x. First, let's start with the Poisson PMF, which you can see right here. Second, we set up our 0 events problem. The average rate for our new interval is the original rate lambda times the length of the interval x. And we want to find the probability of k equals 0 events. Third, we just plug those into the Poisson formula. Look at this equation. The average is now lambda times x raised to the power of 0 times e to the power of negative lambda x, all divided by 0 factorial. Well, anything to the power of 0 is just 1, and 0 factorial is also 1. So the whole thing simplifies beautifully. The probability of 0 events is just e to the power of negative lambda x. And because the two questions were the same, we've found it. The probability of waiting longer than x is e to the power of negative lambda x. Now, this tells us the probability of waiting longer than x. But we usually want the probability of waiting less than or equal to x. That's the CDF, the cumulative distribution function. And it's just the opposite. Check out the formula. It's simply 1 minus the probability of waiting longer. So the CDF is 1 minus e to the power of negative lambda x. This is the one you'll use most often. And if you want the PDF, the probability density function, you just take the derivative of the CDF. As you can see, that gives you lambda times e to the negative lambda x. See? It's not magic. The exponential distribution is born directly from the logic of the Poisson. Let's try a problem. A critical server fails at an average rate of 0.5 times per year. So lambda is 0.5. What is the probability that it fails within the first 6 months, or 0.5 years? Okay, So we want the probability that the waiting time x is less than or equal to 0.5. That's a job for the CDF. Let's look at the formula. We just plug in our numbers. Lambdas is 0.5, and x is also 0.5. So it's 1 minus e to the power of negative 0.5 times 0.5. That's 1 minus e to the power of negative 0.25. Running the numbers, that gives us about 1 minus 0.7788, which equals 0.2212. There is a 22.1% chance the server fails within the first 6 months. And now for the final, beautiful connection. The expected waiting time, or the mean of the distribution, it's just 1 over lambda. This is perfect. It's the inverse relationship we'd expect. It just makes sense. Think about it. The faster the rate, the shorter the wait. If the rate of calls, lambda, is 5 per hour, then the average time between calls, the mean, is 1 divided by 5, or 1/5 of an hour. That's 12 minutes. This relationship makes the exponential distribution absolutely essential for all sorts of fields. In reliability engineering, for modeling component lifetimes. In service industries, for the time between customer arrivals. And even in physics, for things like radioactive decay. We've done it. From coin flips to patterns of growth, we've mastered the 10 essential distributions. 1 hour to master probabilities landscape. And look how far you've come. We went from uniform basics, to normal averages, to exponential waiting times. All 10 distributions. One single, connected story. And now, I want to give you your decision cheat sheet. This is how you go from formula to true intuition. If you remember just one thing from this entire hour, let it be this. Every distribution tells a story about how randomness is generated. The formulas? They're just the grammar. You now understand the story. Look at this cheat sheet. It connects the question you're asking to the tool you should reach for. If you want to model a single yes-no event, you're asking success or failure, one single time. You should reach for the Bernoulli. What if you want to know how many successes you'll get in a fixed number of tries? Well, that's the binomial. Or what if you're asking what a process of adding a bunch of random factors looks like? That's the sum or average. And that's the normal distribution. And if you want to model the time between events, like how long until the next customer arrives, you know that's the exponential. This cheat sheet connects every story to its distribution. You've learned to see the hidden architecture of chance. Randomness is no longer a mystery. It's a language. And now, you speak it fluently. Go decode the world.